Imagine waking up to headlines declaring that Einstein was wrong. It might sound like science fiction or a bad joke, because how could a framework as successful as general relativity be wrong? After all, this is the model that reshaped our understanding of gravity, a pillar of modern physics tested for more than a century. Yet beneath the triumphs lies a profound mystery. Physicists have long suspected that, magnificent as it is, the relativistic picture cannot be the final answer. We already have strong reasons to think something is missing at the deepest level. Today, we will explore why the scientific community is convinced that Einstein's theory of gravity, for all its successes, is incomplete, and why a new framework called quantum gravity may eventually supersede it. General relativity is nothing short of a masterpiece. Introduced by Albert Einstein in 1915, it reimagined what gravity is. Before that breakthrough, Isaac Newton described a force pulling objects toward one another. Newton's law worked extremely well for falling apples, planetary orbits, and sending rockets to the moon. The 20th century insight was that gravity is not a mysterious pull, but a property of space and time themselves. In this view, massive bodies curve the fabric of space-time. Picture a flexible sheet like a trampoline. A heavy bowling ball makes a dent. A marble rolling nearby spirals inward, not because it is yanked by a string, but because the surface is bent by the ball's presence. The sun shapes the geometry around it, and Earth follows those curves rather than being tugged by an invisible wire. Matter tells space-time how to curve, and space-time tells matter how to move. Strange as the idea sounds, the theory has been confirmed by an impressive array of observations. An early triumph came in 1919 during a total solar eclipse. A team led by Arthur Eddington measured how starlight passing near the sun appeared slightly displaced. The light was bent by the sun's gravity, just as predicted. That deflection made headlines around the world and turned the theory's author into an instant celebrity. It was only the beginning. In the decades since, evidence has only grown. We see gravitational lensing, where massive galaxies or clusters bend and focus light from more distant sources. The effect can produce multiple images of a single quasar or long arcs that stretch across the sky. The so-called Einstein rings and doubles are exactly what the relativistic model predicts when gravity acts as a cosmic lens. This is not merely a neat idea. Astronomers have photographed many examples, turning lensing into both a natural telescope and a vivid confirmation that space is warped by mass. The same framework tells us that time does not flow at a universal rate. It runs slower in stronger gravitational fields. This effect, known as gravitational time dilation or gravitational redshift, has been measured repeatedly. In the 1960s, the Pound-Repka experiment detected a tiny shift in the frequency of light as it climbed a tower, exactly as expected, because moving upward in Earth's field makes clocks tick a little faster. Today, engineers must account for this in everyday technology. GPS satellites orbit where gravity is slightly weaker than at Earth's surface, so their clocks run faster than ours on the ground, while their motion slows them down, according to special relativity. Without both adjustments, your phone's position would drift by several kilometers per day. Without the modern theory of gravity, navigation would not work properly. What about extreme gravity? The field equations excel there too. They imply that if enough mass is packed into a small region, space-time becomes so distorted that a boundary forms from which nothing, not even light, can escape. That is a black hole. The idea once seemed bizarre, yet the evidence is now overwhelming. At the center of the Milky Way, stars whip around an invisible supermassive object that emits no light. Their rapid orbits reveal a mass of about 4 million suns. Many other galaxies harbor similar behemoths. In 2019, the Event Horizon Telescope delivered a breathtaking milestone. For the first time, astronomers captured the silhouette of a black hole, the supermassive object in the galaxy M87, about 55 million light-years away. The image showed a bright ring of light from hot gas spiraling close to the hole, and a dark central region where gravity is so intense that light either orbits or falls inward. The size and shape of that ring matched the expectations of relativistic gravity near the event horizon. It was a triumph, seeing the unseeable and finding that even at the brink, the calculations held. Another remarkable prediction of general relativity is that accelerating masses generate ripples in space-time called gravitational waves. In 2015, a century after the theory was born, scientists detected them directly for the first time. Two huge instruments named LIGO measured a faint tremor passing through Earth that stretched and squeezed distances by less than the width of an atom. The signal came from two black holes spiraling together and merging billions of light years away. Its shape matched the predicted pattern with astonishing accuracy. Since then, LIGO and the European detector Virgo have recorded many more events from merging black holes and neutron stars, each detection confirming the relativistic description of gravity under conditions no laboratory can reproduce. From the bending of light to the slowing of time to the reality of black holes and the faint murmur of their collisions across the cosmos, this framework has been tested repeatedly and has passed with flying colors. It is no exaggeration to call it one of the most successful achievements in science. So, with all that going for it, why would anyone say it is not quite right? Questioning such a masterpiece may sound heretical, yet in science, no idea is sacred. What matters is internal consistency and agreement with all of nature. Here, we meet a serious problem. For all its successes, general relativity does not mesh smoothly with another crown jewel of physics, quantum mechanics. Quantum mechanics is the framework that describes the other fundamental forces of nature, besides gravity, and all the known particles. Where general relativity handles the cosmic scale, planets, galaxies, the fabric of space-time itself, quantum mechanics deals with the microscopic scale, atoms, electrons, photons, and all the weird phenomena that come with them. It's hard to overstate how well quantum mechanics has been tested too. Quantum theory underlies the behavior of semiconductors in your computer chips, the fusion reactions powering the sun, the chemistry of molecules, and much more. It gave us lasers, transistors, and has predicted countless experiments with unfailing accuracy. But quantum mechanics is a very different kind of theory from general relativity. It introduces fundamental uncertainty and probability. Particles can exist in superpositions of states, like being in two places at once, in a sense, until you measure them. And outcomes are not deterministic but given by probabilities. It's a theory that even Einstein himself found unsettling. He famously remarked, "God does not play dice," expressing his discomfort with the randomness at the heart of quantum physics. Random or not, quantum mechanics has proven correct time and time again. The trouble is, general relativity and quantum mechanics just don't fit together in one framework. Each works exceedingly well in its own domain. But when you try to combine them, especially in conditions that involve both enormous mass and tiny scales, like the center of a black hole or the very early universe, they seem to conflict. It's like two puzzle pieces that individually complete different sections of a big picture, but that have jagged edges that refuse to snap together. We need a bigger puzzle board, a broader theory that encompasses both as special cases. Physicists call that hoped-for theory, quantum gravity, meaning a description of gravity that follows quantum principles. We don't have such a theory yet, at least not a proven one, but we're pretty sure it must exist, because there are clear signs that general relativity on its own is incomplete. It's one of those situations where nature is giving us hints. A puzzle piece that doesn't fit means the puzzle isn't complete. Let's go through the three major reasons why scientists are convinced we need a theory of quantum gravity. One major reason arises from a simple thought experiment. Call it the double-slit dilemma. What happens to gravity when a particle seems to be in two places at once? One of the easiest ways to appreciate the conflict between general relativity and quantum mechanics is to think about the famous double-slit experiment. If you've never heard of it, the double-slit experiment is a classic demonstration of quantum weirdness. Imagine you have a tiny particle, like an electron, which has a little bit of mass, and you fire it toward a barrier that has two narrow slits cut into it. On the other side of the barrier is a screen that can register where the electron hits. If you cover one slit and fire electrons one at a time through the open slit, they hit the screen and gradually form a pattern just behind that slit, as you would expect, kind of like shooting tiny BB pellets through a hole. But here's the strange part. If you open both slits and again send electrons through one at a time, something almost magical happens. Each electron seems to interfere with itself, as if it went through both slits simultaneously like a wave. On the screen, you don't get two clumps of hits behind the two slits. Instead, you get a series of light and dark bands, an interference pattern, just as you would if waves of water or light were passing through two openings and interfering with each other. Yet these are individual particles arriving one by one. It's as if each electron is in a ghostly both slits at once state and creates an interference pattern with itself. Only when you actually measure or observe which slit the electron goes through does the spell break. The electron then appears to have gone through one specific slit, and the interference pattern disappears. In quantum mechanics, we say the electron was in a superposition of going through slit A and slit B until it was measured. This experiment has been done with electrons, photons, atoms, even molecules consisting of hundreds of atoms. And every time, as long as you don't detect which path the particle took, it behaves like it took all paths and creates an interference pattern. It's mind-bending, but it's our reality. Now, here's the million-dollar question. What about gravity in such a scenario? If an electron or any particle can literally be in two places at once in a quantum sense, where is its gravitational pull? We know an electron has mass, albeit a tiny amount. And according to general relativity, any mass curves spacetime and creates gravity. So if the electron goes through both slits at once, does it create two overlapping gravitational fields? Does the gravitational influence also go into a weird superposition of two paths? In general relativity, gravity isn't something that can be in a quantum superposition. The theory treats space-time as a smooth fabric and mass energy as something that warps that fabric. It doesn't have a built-in way to say, what if the mass is kind of here and kind of there at the same time? In Einstein's classical gravity, an object has a definite location and its gravitational field smoothly fills space around it. So, if we insist on keeping gravity classical while the electron is quantum, we hit a paradox. Suppose the electron really does go through both slits in superposition. If the gravitational field remained classical, it might have to choose a configuration. Perhaps the equivalent of the electron being in one definite place or the other. But that would actually be a measurement on the electron, because gravity affects the electron too, forcing it out of superposition in contradiction to what quantum mechanics predicts. On the other hand, if the gravitational field somehow follows the electron's quantum behavior, then effectively, the gravitational field itself would have to be in a superposition spread over two paths. But we have no way to describe a gravitational field being in two states at once using general relativity. That's a quantum concept. Gravity, in Einstein's formulation, doesn't have probabilities or superpositions. It just is, shaping space deterministically around masses. This conundrum might sound philosophical, but it has real consequences for consistency. If gravity stayed classical while matter is quantum, in principle, one could use the gravitational field to gain information about the particle's position without touching the particle, potentially violating the uncertainty principle or other quantum tenets. Most physicists find that idea suspect. It would allow too many loopholes to the quantum rules that have never been seen to fail. The safer bet is that gravity itself must eventually obey quantum rules if we examine it at small scales or in delicate setups. Now, here's an important point. We haven't yet observed this conflict directly in an experiment. We haven't taken a single electron in a double slit setup and measured its gravitational field in two places, because the gravitational forces involved are incredibly, ridiculously small. Gravity is by far the weakest of nature's forces, and an electron's gravity is so weak, it's essentially impossible to detect with current technology. So we can't just do an experiment with one electron's gravity to see what happens. But thought experiments like this guide us. They tell us there's an inconsistency in our theories. Quantum mechanics says the particle can be in two places. General relativity says mass can only curve space-time from one place at a time. They can't both be right in this scenario. To resolve that contradiction, we expect that gravity must have its own quantum behavior. In other words, space-time itself would have to be able to exist in a superposition or show uncertainty at very tiny scales. The idea at the heart of quantum gravity. Interestingly, physicists are getting creative and starting to design experiments that, while not looking at single electrons' gravity, might test the quantum nature of gravity in other ways. For instance, there are proposals to use two slightly larger masses, like tiny microspheres, and put them each into a quantum superposition at different locations, then let them interact gravitationally. If the two masses become mysteriously entangled, a quantum connection, with each other due to gravity, that would be a sign that gravity had to be acting quantum mechanically, because entanglement is a quantum phenomenon. Such experiments are extremely challenging and have not yet reached the sensitivities needed, but they illustrate the point. Most scientists believe gravity isn't exempt from quantum rules. If every bit of matter and energy follows quantum laws, and gravity is nothing but the manifestation of that matter and energy bending space-time, then space-time should ultimately have a quantum description too. Einstein's classical picture of smooth, definite space-time distances and curvatures will have to give way to a picture where space-time can jitter, fluctuate, and exist in multiple states, concepts that only make sense in quantum mechanics. Another compelling reason comes from looking at where general relativity itself breaks down, the riddle of singularities. The second big reason we think general relativity can't be the final word is that left to its own devices, it predicts its own failure in certain situations. Specifically, it produces what we call singularities, points or regions where some physical quantity, like the density of matter or the curvature of space-time, becomes infinite. Infinity is a huge red flag in physics. It usually means, "Here be dragons," meaning our equations have gone beyond where they are valid. Let's talk about the two most famous kinds of singularities in general relativity: the center of black holes and the moment of the Big Bang. We've already touched on black holes. According to Einstein's theory, if you collapse enough mass into a small region, space-time warps more and more until at some point a horizon forms beyond which not even light can escape. Now, once matter passes inside that event horizon, the black hole's boundary, the theory says it continues to collapse toward the center. In the classical version of the theory, nothing halts that collapse. There is no force that can counteract gravity at that point. The equations indicate that all the matter gets squashed into an infinitely small point at the very center, a point of infinite density and infinite space-time curvature. That is the singularity at the heart of a black hole. It's not a place in space you could locate on a map. It's more like the end of space and time, where our ability to describe what's happening just fails because numbers like infinite start popping out of the equations. Now, no one believes that this infinite density point is literally what exists inside a black hole. Instead, physicists interpret this as a sign that the theory, general relativity, has reached the edge of its applicability. It has encountered a condition so extreme, mass and energy crunched to an arbitrarily small volume, that the assumptions of the theory break down. A similar thing happened in physics before. For example, in classical pre-quantum physics, if you tried to calculate how much energy is radiated by a hot object using classical electromagnetism, you'd get an infinite amount of energy coming out at high frequencies, the infamous ultraviolet catastrophe. The resolution to that paradox was the birth of quantum mechanics. Max Planck and others realized that energy comes in discrete quanta, which put an end to that infinity and produced a finite result that matched reality. In other words, the classical theory, Maxwell's electrodynamics plus classical thermodynamics, was incomplete at small scales, and quantum physics fixed the problem. We suspect something similar with gravity. The singularity at a black hole center is like a giant warning sign saying, nature doesn't actually do this. Something new physics, must happen here. The other famous singularity is the Big Bang. If you run the cosmic clock backward according to general relativity, the universe gets denser and hotter as you go earlier in time, which matches what we observe up to a point. Early in the universe, things were indeed hot, dense, and rapidly expanding. But if you go all the way back to time zero, the math suggests the universe was compressed to a point of infinite density and temperature. Again, a singularity. In the classical theory, that's the beginning of time and space. You can't talk about before, because time itself somehow starts there, and everything is infinitely dense at that initial moment. Once again, physicists doubt that this is literally what happened. More likely, this is telling us that the classical framework, without quantum corrections, breaks down at around that point, specifically at exceedingly high densities and tiny scales, far smaller than any atom or particle. If we had a quantum theory of gravity, we think it would smooth out the singularity or avoid the infinity, giving us a finite, sensible description of what happened at the start of the universe, or even an alternative to the start as a singular moment. Imagine zooming in on the fabric of space and time at extremely small scales. General relativity treats space-time as smooth and continuous, like a perfectly flexible rubber sheet. But we already know from quantum mechanics that at tiny scales, the idea of smooth continuity often breaks down. Energy comes in quanta, and fields can fluctuate. So, many researchers suspect that if we zoom in far enough, space-time might have an atomic or quantum structure. We sometimes call this the quantum foam picture. At the Planck scale, the unimaginably tiny scale of about 10 to the power of minus 35 meters, space and time might be wildly fluctuating, probabilistic, or discrete. If that's true, then asking that theory to handle an infinitely small point is like asking an old map to show details smaller than the ink's grain, and it is just not equipped for that resolution. A down-to-earth analogy is hydrodynamics, the theory of fluids, versus molecular physics. Equations of fluid dynamics are very useful for describing things like airflow or water waves, and they treat fluids as continuous substances. But if you push those equations too far, you might get a non-physical result. For example, when a drop of water pinches off from a faucet, the equations could predict an infinitely sharp neck forming at the breakpoint, a kind of singularity in the math. In reality, of course, water is made of molecules. You can't compress water into an infinitely thin thread. At some point, the discrete molecular nature and other physics steps in, and the singularity is avoided. Similarly, we believe that on scales where spacetime's atoms, whatever they may be, become important, the singularities of general relativity will be resolved. No infinite densities. Instead, something new happens. So, singularities are like signposts telling us general relativity stops here. Beyond this, we need a better theory. Whether it's the center of a black hole or the origin of the universe, these are domains where gravity is incredibly strong and matter is incredibly compressed, exactly when quantum effects can no longer be ignored. Only a theory that merges quantum mechanics with gravity could describe what goes on in those extreme environments. For instance, a working theory of quantum gravity might reveal that black hole cores aren't infinitely dense points at all, but perhaps some exotic state of matter, or a bounce to another region of space-time, or something we haven't even imagined. Similarly, the Big Bang might not be the beginning in a quantum gravity scenario. It could be that the Big Bang was a transition from a previous cosmological phase or collision of membranes, as some versions of string theory propose, or a quantum fluctuation that sparked inflation. There are many ideas, but we can't know which, if any, is right until we have the fundamental theory in hand. In short, the existence of singularities in general relativity is a glaring indication that the theory is incomplete. When you get to the most extreme realms, Einstein's equations essentially fold their hands and give up by spitting out infinities. Physics has been here before with other theories, and each time, the way forward was to develop a deeper theory that handles the extreme conditions. For gravity, that deeper theory is expected to be quantum gravity. And the third key reason is the famous black hole information paradox. Essentially, a fight between relativity and quantum mechanics. Our third reason is a kind of 1-2 punch combination of the first two. It's what happens when you apply quantum thinking to a gravitational system and find a fundamental inconsistency. It's called the black hole information paradox, and it was first widely discussed in the 1970s after Stephen Hawking made a startling discovery. We've mentioned that according to general relativity, nothing can escape from inside a black hole's event horizon. If you fall in, you're not coming out. But in 1974, Stephen Hawking was studying what happens when you add quantum mechanics to the mix. Specifically, what happens to quantum fields, like the electromagnetic field, for instance, near the event horizon of a black hole. He found something amazing. Black holes aren't completely black. When you include quantum effects, black holes should emit a very faint glow of particles, now known as Hawking radiation. How does that work? The simplest way to picture it is this. Even what we think of as empty space is not truly empty. Thanks to quantum uncertainty, the vacuum is teeming with transient particle-antiparticle pairs that pop in and out of existence briefly. Normally, these pairs annihilate each other almost immediately, and you never notice them. But Hawking realized that at the edge of a black hole, the intense gravity could separate these pairs. Imagine a particle and its antiparticle appearing near the event horizon. One of them falls into the black hole while the other escapes before they have a chance to annihilate. To an outside observer, it looks as if the black hole is slowly radiating particles and losing energy in the process. Another way to think of it, the black hole is converting some of its mass energy into particles that leak away to infinity. Over a very, very long time, this process will cause the black hole to shrink and eventually evaporate completely if it doesn't keep feeding on new matter. Hawking's theoretical prediction of black hole radiation was revolutionary. It connected quantum theory, gravity, and thermodynamics, since black holes were found to have a well-defined temperature due to this radiation. Physics rarely gets more profound than that, but it also presented a profound problem. Hawking radiation, as he calculated it, is thermal radiation. That means it's essentially random, carrying no detailed information about what's inside the black hole. All Hawking radiation cares about is the mass, spin, and charge of the black hole as a whole, which determine the temperature of the radiation. It doesn't encode whether the black hole formed from a collapse of a star or from a pile of burning textbooks or anything specific. Two very different things that form identical mass black holes will produce exactly the same Hawking radiation as they evaporate. So as a black hole radiates away and loses mass, it's like it's slowly erasing itself. Now, suppose you have a black hole that forms from some collection of matter, and then over an incomprehensibly long period, far longer than the current age of the universe, if it's a stellar mass or larger black hole, it evaporates completely, leaving only a cloud of Hawking radiation that has dispersed into space. Here's the paradox. All the information about what fell into the black hole appears to be gone. You could gather every particle of that Hawking radiation and study it all you want. All you deduce is the black hole's mass, spin, and charge, but not a single detail about what was inside. If a black hole swallowed an encyclopedia, or an elephant, or a heap of uranium, it wouldn't matter. The final Hawking radiation is totally generic. It seems as if the information that went in is lost forever. Why is that such a big deal? Because it seems to fundamentally violate a core principle of quantum mechanics. In quantum physics, processes are reversible in a particular sense. If you know the exact state of a system at one time, there is a well-defined way, the Schrödinger equation, or its quantum field equivalent, to evolve it forward and backward. You could, in principle, reconstruct the past from the present state. Information is preserved. It may get scrambled or hidden, but it's not destroyed. For example, if you burn a letter, you might say, well, the information in that letter is lost. But a physicist would counter, in principle, if you had the positions and velocities of every molecule in the smoke and ash and air and the exact infrared photons radiated away from the fire, you could, again in principle, reconstruct what was written on that paper. The information wasn't destroyed. It was just transferred into degrees of freedom you can't easily track. That's a messy practical example. But at a fundamental level, quantum theory insists on what's called unitarity, which basically means information is never truly wiped out. It just gets moved around or entangled in different ways. No known experiment has ever violated this principle. Yet, a naive reading of Hawking's result suggests that information is truly being erased from the universe when black holes evaporate. If you can't, even in principle, figure out what went into a black hole by examining what comes out. That's like having a video of the universe's history that's missing a few pages in the middle. The story wouldn't add up to a consistent reversible process. Hawking himself recognized this problem. For a time, he actually leaned into it, suggesting that maybe quantum gravity would allow a slight relaxation of the rules, and that information could be fundamentally lost. This idea didn't sit well with many others, like physicist Leonard Susskind, who argued that something had to give. Either our understanding of black holes was wrong, or our understanding of quantum mechanics was wrong, and quantum mechanics had never let us down before. This debate went on for decades, and is still not completely resolved, though by now a majority of physicists suspect that no, information is not actually lost. Somehow, if we could see the full picture with a correct theory of quantum gravity, we'd find that the information does come out or never really disappears. How might that happen? There have been many ideas. One is that maybe Hawking's original calculation, which treated gravity classically and matter quantum mechanically, missed some subtle way in which the outgoing radiation is not perfectly featureless, that it does carry a hidden imprint of what fell in. Another idea is that black holes don't fully evaporate, that perhaps they leave behind a stable remnant, a tiny nugget of something containing all the information, though that raises other issues. Yet another suggestion is the holographic principle, which emerged from string theory and black hole physics. It proposes that all the information that falls into a black hole is not lost at all, but rather stored on the event horizon's surface, much like a hologram encodes a three-dimensional image on a two-dimensional film. And as the black hole evaporates, this information somehow trickles out with the radiation in an encoded form. There was even a dramatic proposal that maybe to preserve information, an energetic firewall forms at the horizon that breaks the semi-classical description we have, though that idea itself leads to other paradoxes. It's a rich field of theoretical debate. The details of these proposals get very deep into physics, but the overarching point for our story is, without a full theory of quantum gravity, we can't be sure which resolution, if any of the above, is correct. What we do know is that the semi-classical approach, using quantum theory for particles and fields, but classical general relativity for space-time, gave us a paradox. It gave us a scenario in which our two fundamental theories give contradictory expectations. That tells us the semi-classical approach is at best an approximation, and it breaks down in this scenario. So, just as singularities signal a breakdown of the classical theory, the information paradox signals a breakdown of using classical GR in a quantum context. We need the real deal, a quantum gravity theory that treats the gravitational field itself quantum mechanically, so that we can properly analyze something like a black hole evaporating without losing track of information. Stephen Hawking himself eventually came around to this majority view. In 2004, he conceded a famous bet he had made with physicist John Preskill, and acknowledged that he now believed information is not lost from black holes, that somehow quantum gravity must preserve it. It was a poetic turn. Hawking, who had uncovered the paradox, recognized that the resolution lies in a better theory that we don't yet have in full. To put it simply, we have three strong arguments that gravity must bow to quantum rules. 1. Quantum objects can do things, like being in two places at once, that a classical spacetime can't accommodate. 2. Einstein's theory produces nonsensical infinities in certain extreme situations, which usually signals the need for new physics. And 3. If you try to meld quantum theory with classical gravity, you get logical contradictions, like the black hole information paradox. which suggest that only a fully quantum version of gravity will make everything consistent. Each of these reasons alone is compelling. Put them together, and the case is overwhelming that Einstein's general relativity, despite all its triumphs, is not the final story. It is a fantastically good approximation that works in almost all circumstances we can observe, but it fails in the most extreme situations we can imagine. It's very much like how Newton's classical gravity is an approximation to Einstein's. Newton wasn't wrong for the realm of falling apples and orbiting planets, but his theory had to be expanded for regimes involving high speeds or strong gravity. Similarly, general relativity will need to be expanded or replaced when we deal with the quantum realm. We anticipate that, in the grand scheme, general relativity will turn out to be the large-scale, smooth limit of a deeper quantum description of space-time. The quest for a theory of quantum gravity has been underway for many decades now. It's often touted as the holy grail of theoretical physics, a single framework that unites the physics of the very large, cosmology and gravitation, with the physics of the very small, quantum particles. It's a challenging pursuit, to say the least. One major obstacle is that we currently lack direct experimental clues about quantum gravity. The energies at which quantum gravity effects become significant, the so-called Planck scale, are astronomically high, far beyond what particle accelerators can produce, and the corresponding length scales are incredibly tiny. So physicists have had to be clever and guided by mathematical consistency, as well as whatever subtle hints the universe can give us, like those paradoxes and problems we discussed, which are clues in themselves. There are several promising theoretical approaches. One is string theory, which posits that all particles, including the graviton, the hypothetical quantum particle of gravity, are tiny vibrating strings of energy. String theory has the attractive feature that it naturally includes gravity and is quantum from the start. It also, fascinatingly, suggests extra dimensions of space beyond the three we experience. Those extra dimensions might be curled up at very small scales. String theory is mathematically complex and hasn't yet made testable predictions we can verify, but it remains a leading candidate for quantum gravity. Another approach is loop quantum gravity, which takes a more direct route by trying to quantize spacetime itself. In loop quantum gravity, space is not continuous, but made of tiny discrete chunks or loops. Imagine a weave or network structure on the Planck scale. This theory has had some success in, for example, eliminating the singularity inside black holes in its equations, and suggesting that perhaps the black hole's core might transition into something else instead of a point of infinity. It also offers a picture in which the Big Bang singularity is resolved into a big bounce, the universe collapsing and rebounding rather than beginning from a true singularity. However, loop quantum gravity, like string theory, is still under development and lacks experimental confirmation. There are other ideas as well, proposals like asymptotically safe gravity, causal dynamical triangulations, emergent gravity approaches, and more. The fact that we have multiple approaches but no consensus yet tells you how difficult this problem is. Nature isn't giving up her deepest secrets easily. So where do we stand? We know what the problem is. General relativity and quantum mechanics must be reconciled. We know why it's necessary. Without quantum gravity, we have logical inconsistencies and unanswered questions about singularities and black holes. The challenge is figuring out the how. In the meantime, physicists are also looking for ways to test quantum gravity theories. They scan the cosmos for hints. For example, some theories predict a very slight breakdown of Einstein's predictions at extreme conditions, or perhaps a tiny granularity of space that might blur the images of distant high-energy events. So far, no clear sign of quantum gravity has appeared, but the search continues. We might also learn more from cosmological observations. The way the universe expanded in its first fraction of a second might carry fingerprints of quantum gravity. Some subtle statistical patterns in the cosmic microwave background, the afterglow of the Big Bang, could hint at quantum gravity effects during the universe's birth. The effort to unify general relativity with quantum mechanics is not just about fixing equations. It's about deepening our understanding of reality. Think of what happened when we unified electricity and magnetism in the 19th century. Maxwell's theory gave us electromagnetic waves, and hence radio and much more. Or when we combined quantum mechanics with special relativity, Dirac's theory predicted antimatter. Unifying quantum physics with gravity could lead to equally revolutionary insights. It might tell us what really happens at the edge of a black hole or at the birth of the universe. It could reveal whether space and time are emergent phenomena rather than fundamental ones. It might even open up possibilities of technologies we can't currently imagine. Though speculation about quantum gravity tech is very premature, since we don't yet know the basics of how it works. At the very least, achieving a theory of quantum gravity will mean we have a single framework that doesn't break down or give nonsense, no infinities, no paradoxes, in any situation, no matter how extreme. It would be the ultimate synthesis of Einstein's cosmic insights and the quantum pioneer's microscopic insights. Einstein himself spent the latter part of his life searching for a unified theory that could merge gravity with the rest of physics, though in his time, quantum mechanics was still developing, and he never embraced its indeterminacy. It's ironic that the path to fulfilling Einstein's dream of unification likely requires fully accepting the quantum nature of reality, dice and all. If he were alive today, perhaps he would be skeptical of some of these ideas, but he would surely be fascinated by the effort to quantize the very space-time he so elegantly described. In conclusion, Einstein's general relativity has been an extraordinarily successful theory, and for everyday purposes and even extreme astrophysical conditions, it works brilliantly. But like every theory in science, it has its limits. We know those limits are there. We see the cracks when we bring quantum mechanics into the picture. Whether it's the puzzle of a particle in two places at once gravitationally, the mathematical breakdown at singularities, or the paradox of information seeming to vanish in black holes, each clue points toward the need for a deeper theory. Physicists are confident that general relativity is not wrong in the sense of being thrown out, just as Newton's laws are still valid in their domain. Rather, general relativity will end up as a special case of something bigger. Quantum gravity, whatever form it ultimately takes, will reduce to Einstein's theory in normal, low-curvature situations, just as Einstein's reduces to Newton's under ordinary conditions. But in the new theory, when we venture to the edge of a black hole or back to the birth of the cosmos, we won't hit a wall of infinities or paradoxes. We'll have equations that make sense, and perhaps even new predictions we can test. Einstein's work solved so many mysteries, yet opened up new ones. Solving the puzzle of quantum gravity could be the next giant leap, one that answers old questions and no doubt reveals new wonders. We don't know when it will happen. Perhaps tomorrow, a genius will have a breakthrough, or perhaps it's still a century away. But human curiosity and ingenuity, being what they are, we keep chipping away at the problem. And one day, we'll look back at general relativity and quantum mechanics not as incompatible rivals, but as harmonious parts of a single grand theory of how the universe works. Until then, we live in the fascinating in-between, knowing something's not quite right, driven to find the answer, and marveling at the fact that even our greatest theories can evolve into something even more profound.